Swayam Prabha. Digital India. Educated India.
Okay, I plan on spending another 10 minutes on collision and move on to the next topic. This is just a repetition of what I showed earlier. And here the same collision kernel, geometric collision kernel for gravity, or bigger particle going down. And if you have a nice linear shear flow like this, collision kernel is given by this, because obviously relative velocity doesn't matter. It's only a question of how much is the shear and where the size of the particles. Now G is the shear. Turbulence collision kernel, you just plug in this value of G, because turbulence is essentially shear collision, and the effective shear in a turbulent flow depends on eddy dissipation. Epsilon is the dissipation. So you look at, if you're doing Rand's model, you know what the local dissipation is, and you take the dissipation, multiply by 3 pi divided by 10 times the kinematic viscosity of the fluid, and you calculate this and you get G. Okay. So this basically is a summary of all the geometric collision kernels. Okay. So you really have to take these things and multiply by collision efficiency and coagulation efficiency. The other thing I wanted to show was this. This is the same equation that we wrote as summation, but written now as integrals. Previously we used M, monomer size 1, 2, 3. Now obviously there is nothing called a monomer. So here instead of M we have volume of the droplet. That this V is the volume, and this volume can be very small, corresponding to a sub-micron droplet to 10, 100 micron droplet. And this n of V of t here, remember, since V is a continuous variable, this is the number of droplets or particles of size V less since it's continuous, it is V minus dV by 2 to V plus dV by 2. So in other words, this is the number of particles in a bin of size, because there is no more meaning to say what's this volume, because you have to now think in terms of a bin. Okay. So around V, if you take a little dV, that dV is the size range. How many particles are there, droplets are there, that's this term. And why it changes? Well, new ones are being produced, existing ones are being consumed, and there is a separate source. And that source is what I was talking about, was in rain formation in a cloud. You will have new nucleation sites, and typically the source will be far for very small V. Large ones don't get nucleated. Okay, large ones produced only because of collisions of smaller ones. So people track this, and some of you are doing in your research. Okay. So you get, if you plot n V as a function of V, you will get a nice spectra like this, like a turbulent spectra. You will get yeah. So in other words, you will have one size where there is a lot of droplets, and you go to larger and larger ones, you're going to. So one of the important things, just like in turbulence, is that how n goes N is a power law because this is a log scale. So one of the interests is what's the slope of that sort of an inertial kind of range. Okay, so and that depends on whether you have collision dominated by gravity, because you see the dependence on volume, these are all volume, dependence on volume changes from whether it's a shear collision or whether it's gravity collision, etc. And if gravity is dominating, the slope will be something. If instead turbulence is the biggest collision mechanism, then the slope may be slightly different. Okay, and there could be fairly interesting competition. So if you think in terms of, actually this is not a bucket, you should think more in terms of, say, cloud. Small droplets are continuously being produced, large ones are settling out of the cloud as rain precipitation. How the small ones become large ones is due to collisions. Therefore, one of the biggest challenge, which still remains a challenge, is our inability to predict rain. See, when you notice here, maybe in India it's not that big a deal because you just have to say hot, or Chennai especially, you just have only two weathers, hot and very hot. There's nothing to predict. So, but there, cold fronts sweep over, and you know, today, especially Florida, is pretty bad, because what happens is that it's 80 degrees, everybody is in, you go to office in your t-shirt, and then as cold front comes, and by evening when you're returning back, it would be really freezing. May not be quite freezing, but pretty cold. So the drop a changing. Now that people predict very well, because it's a very advection problem. So in other words, if a front is coming, say in Indian context, if that cold front comes to Bangalore, it's just a matter of few hours before it sweeps over Chennai. If it's moving there, all the fronts go from in the higher latitudes. All these fronts move left to right. Okay, and therefore you can predict that. But one of the things is that rain formation is the a very difficult thing, and it's also very spotty. Just because it rains in IIT campus doesn't mean that it's going to rain in Adyar or Trivandrum. So this prediction of rain has been a big challenge, and one of the reason is people have a very good idea how small droplets nucleate. That's not a secret. And large droplets, once you get to millimeter size, their velocity is fairly large. So you know, so it's the thing how small ones become large, what's the speed at which that growth happens is a major challenge. And I know India, IISc and a lot of places in India doing excellent research on that because it's probably important here, how the rain, monsoon and so on and so forth. So that's where these kind of research, or at least one application there is. I will skip this detail. So I will stop with this slide. This is a slide by Annual Review of Fluid Mechanics paper by Grabowski and L.P. Wang. What they have here is time here, and on this size, radius in millimeters. Okay, so you can see this is a 1 millimeter droplet. This is 1 millimeter droplet. This is without turbulence, and this is with turbulence. In other words, they change. The details are in their paper. You can read it. Okay. The important thing is that as time proceeds, I don't know what this, maybe it's hour, okay, I don't know. So if you are some non-dimensional quantity. So here you see at very, very late stage, and there are many lines there. Those lines correspond to number of particles. Okay, so in other words, the y-axis, there are two axes. One, there is time, which is different curves. For each curve, it is number of droplets of a given size. So if you have a big peak around 1 millimeter, that you have produced 1 millimeter droplet. So without turbulence, if you didn't have fast collisions happening. It takes your prediction is that it takes this much time to produce millimeter size droplets. Okay. On the other hand, if you carefully account for all the collisions, collision efficiencies, agglomeration efficiencies, if you do the right job, you do get fairly early onset of a range size droplets, and this is their conclusion. So I recommend that their paper, and there's a lot of other papers by Sundaram and Collins and a lot of things. Just my PhD was on this topic a long time ago, on droplet collisions and coagulations and growth. That's my last slide of this topic. Any questions on that? Yes.
So if we are talking of time simulations and DEM perspective in ideal Lagrangian frame of work, so if we have a domain, let's say some millimeters or centimeters of cube or something like that, then how should I, since all these collision kernels or any of the calculation we do in CFD on a domain in a cell's perspective, so how should I choose my cell size? Because we are accounting not for the volume of the droplets, we are only seeing the source terms which are coming out of the droplet. So how do I choose a cell size basically? Because if a collision is happening, there is a breakup or a agglomeration, because of that the size of the droplets will vary with time. So how do I choose the size of the mesh?
Yeah. I would recommend that you don't need to choose your size based on collisions and coagulation, because collision and coagulation, we are not tracking particles here. You don't need Euler-Lagrange, right? So all these things, that's an excellent question. If you're doing DEM either with resolved particles, but more likely, let's say, with Lagrangian particles, you're tracking particles, you can watch them collide, because if their centers get closer than one diameter, the sum of these two radii, then you will say, okay, you use soft sphere collision model or hard sphere collision model, implement that. Or you could say, in case of droplets, well, then here is where the magic comes. Okay, even in particle resolved simulations, the very close interaction, the contact mechanics, must be modeled, soft sphere, hard sphere, for bouncing part. Now, if you are using droplets, you got to use some empirical relation to say, I'm going to put them together as one bigger droplet. So you have to put only collision efficiency and coagulation efficiency, just like what I showed. Only thing is that you don't need any more geometric collision kernel, because it's there. Geometric collision kernel is needed only when you do Euler-Euler simulation, because you don't have tracks of individual particles, but in your cell you know what is number of particles of one size. So let's say you're tracking 5 different size particles. So like I earlier wrote, n of the first size times n of the second size times collision kernel, you can use that to keep account of how many particles or droplets of each size is there in your finite volume cell. Okay. So now your question is, how big a cell should you choose? I would say let other considerations dictate that. Okay. You choose it according to what computation you have, etc. But since this collision kernel is an average one, if we are going to have only one particle or two particle in there, the noise will be so much in that cell. But if your cell is fairly big, that you have few hundred to few thousand droplets, then the predicted number of collisions will be more robust. See, the rule is always, when you have few and you're using average to model that very few, you can be off by a big amount. But if your cell is fairly large and there are lots of collisions happening and you're using this model, Its model is fairly accurate to predict the thing. So you shouldn't use very small grid. If you're going to do an Euler-Euler simulation, if you're going to use a very fine grid, you might as well track the particles and collide. So that may be a sort of a broad guidance I might provide. Okay.
Like we talked about various collision efficiency, so these are valid for coagulation kind of thing. If we are considering breakage in our equation to R, will these also be valid?
No. Okay, excellent question. So I will save a couple of minutes on breakage. Okay. So breakage will involve. We had term 1, 2, 3, 4, or in Smoluchowski's equation, we had only 2 terms. Okay, so we have written that. Now this only accounts for how number changes because collisions. Remember, this itself have a source and a sink. Each collision can take you away from your size, current size. Now breakup, same thing happens. There will be 2 terms. A breakup of size V could create 2 smaller sizes. So for the smaller sizes, breakage will appear as a source term. For size V, it will be a loss term, so it will come with a negative sign. On the other hand, a size V droplet, volume V, can be produced if somebody bigger breaks up. So there will be 2 terms. Now you can ask, okay, that's great. So there are 2 new terms with breakup. Just like C, what is going to be there? Okay. So there are 2 things. For breakup, there are 2 items that you need. Here only collision kernel, which inside has collision efficiency and coagulation efficiency. But for breakup, typically you need 2 things. The breakup rate. What is the rate at which a droplet will break up? That depends on the size and the shear and so on. So who is going to break up, right? So usually droplet breaks up because of shear, okay, and it's a very complicated process, okay. The second thing that you need to know is breakup spectra. So in other words, what droplet, a daughter droplet size you will create out of each breakup. That's also a stochastic quantity. So the conclusion is that in the Smoluchowski's equation, you will have 2 additional terms, okay, 1 plus, 1 minus, and those 2 terms will involve 2 models. One, what's the rate at which a breakup happens, and when a breakup happens, what's the probability of the daughter droplet sizes. If you can get those 2 things, there are lots of models there. You put them, you can take care of growth due to collisions and breakup, and this is what somebody was saying, Ramakrishna, population balance. So very nice. I mean, follow their work. They are the leaders, and yeah.
So we will include that collision kernel. Like by collision kernel, we can include this, no, like how the particles are colliding with each other. Yeah. Then we multiply the breakup term. That will define the breakup, and then we'll multiply the PDF probability distribution function. So these all 3 together will it give the kernel for breakage? If we
no breakage. Well, I don't think you need to worry about. Well, you know, the breakup happens sometimes due to collisions, but most of the droplet problems, breakup happens because of shear. Turbulence just rips it apart. Okay, so if breakup is due to turbulence, then collision is not an issue. Okay, so when I was talking about it, I was talking only in terms of breakup rate due to turbulent shear as opposed to collision induced breakup. Yeah. Okay. Then the breakup kernel won't have anything to do with collision kernel. Okay, but if collisions are the ones who are breaking things up, then you have to combine them in some ways. Okay. So first, I want to talk about the benefit of filtering. Okay. So let's say you have a turbulent flow in a box, and you have lots of millions of particles in this. It's a multi-phase flow, maybe it's a fluidized bed, okay, with something flow coming from here, suspension of particles and so on. So typically what we are going to do is we are going to have a grid, and you will use finite volume or finite element, spectral or whatnot, different methods you are going to use. That's easy to think in terms of finite volume. So let's go in here and look at this little volume. Now inside this volume you have a lot of particles in there. So they are not necessarily sub Kolmogorov scale, because they may still be bigger than, but they are certainly smaller than your grid size. So in other words, you are resolving only eddies that are as big as your grid, so these are smaller than. Now I call this length scale. So in other words, when you do a computation like this, when you do a LES, whether you actually filtered it or not explicitly doesn't matter, but you have implicitly chosen a length scale which is your grid size, and you are saying, I really don't, I'm not going to compute anything smaller than this. Typically you will not be accurate for anything eddies that are less than 3 or 4. So in other words, eddies you need at least couple of grid points. So only the smallest eddy that you will compute is 2 or 3 grid cells on each side. Okay. But for scaling analysis you can simply say that the grid size sort of sets up the split. In other words, if you take the turbulent spectra, one over L is some length scale or inverse length scale, and you are saying compute, and this must be modeled. Okay. So in other words, I want to think in terms of filtering. The real fluid flow had lots and lots of eddies, and you filtered and you removed, this portion has been removed. This guy is going to affect this guy, and you said, okay, I am going to model that. There are two things that your mistakes we are doing. In other words, remember, even if your model is right, you are only computing part of the turbulence, because you cannot say anything about what is below your grid. All we are in LES trying to do is the best job for those who are we decide to compute by using the best model, but we will never know precisely what is below your grid. So why do we do this? In multi-phase flow, what does it gets us? Two wonderful things. The first one is it has to do with single phase turbulence, which is saying that, look, I'm going to only worry about big eddies, and most importantly, instead of doing a trillion grid simulation, you can reduce it to a million, or so you can make it happen. Okay, that's the biggest advantage. But really, what we are doing is that we are only computing larger eddies. But the second most important thing that happens in this one is you don't have to worry about the flow around each and every particle, because it doesn't make any more sense. That's the biggest advantage. If you were to do particle result simulation, you got to apply no slip, no boundary, no penetration boundary condition on the particle. And as the particle is moving, you got to chase after it, put a grid around it, put immerse boundary. My God, I mean, that's a pain. So really, it's much nicer. So the filtering operation in multi-phase flow, it's like God's gift. because it makes things possible. That's why Euler, Lagrange, Euler are wonderful. If we don't have those methods, we are doomed. Okay? We can only deal with systems that have few thousand particles, which means practically you cannot study anything. But we do. I do a lot of you guys also probably do microscale simulations, but with a purpose, which is, hey, I do microscale simulation not because that's the reality. I do it because I can tell something, I learn something, and I can put it back and help Euler Lagrange or Euler. So filtration is a very important thing. So this lecture is the sort of a foundation for Euler Lagrange and Euler methodology. So please ask me any question as they arise. So two reasons why we do that, and the second reason is the most important, because I don't have to resolve the flow around the particle. That's the biggest advantage. Okay. Now in Euler Lagrange we have to track where the particles are. So in some sense in Euler Lagrange you filter the fluid but not the particle. So there is only one averaging you're doing for the fluid phase, but you try your best to keep the particle phase as much as possible intact. But in Euler, the same thing that we did for the fluids, we will also do it for the particles. So right now you look at this little box that I have drawn. You have only one fluid velocity here. In this box, if you use a finite volume, there is a u vector, there is one temperature there for fluid, but you have velocity for every particle. You may have velocity for every particle, that temperature for every. So in other words, there is no averaging for the particles, but you did averaging for the fluid. Okay. So those are some very basic facts that I wanted to, I mean these are things that you know, so the advantage is that you can relate to what I am talking about. I just sensitizing you to it. So what is this filter operation? So what we want to do is that, hey, we have averaged the fluid velocity for this cell when there is a lot of details in there I am just ignoring. How do I get it? So we want to derive the governing equation for Euler Lagrange and Euler starting from particle resolved approach. So in other words, I am going to write particle resolved equations. I will not be able to compute it, but conceptually I will write it, flow around billion particles. So that's the nice thing. If you don't have to compute it, you can do anything. I mean, you don't have to stop at billion. I can even trillion. I can write it, okay? But then we will formally average it, and that's the filtering operation that we are going to talk about. Okay. So let me go here. So what we do is that here we have a box. I'm looking at one finite volume cell where there are particles in there, and I briefly talked about indicator function. This is the continuous phase indicator function. So this x is nothing but the position of this finite volume cell, and the time is whatever time. So this indicator function says in this cell at this x location at this time it will pick where the fluid is. This is subgrid. This x is, now I am thinking in terms of subgrid. Inside this finite volume I pick different points here, and I can find, am I in the fluid, am I in the solid, and this is the indicator function, which is 0 inside particle, 1 inside fluid. And I can similarly define whether I am inside the particle or inside the fluid, and here it will be 1 and 0. And then indicator function for the continuous phase and the dispersed phase must add to 1. Here I am only talking about two phases. There are only solids and fluid. Now what we are going to do is that the other thing that I am going to define is there are different filtering operations, but I am going to define a Gaussian filter. It is a 3-dimensional filter and it's a product of 3 one-dimensional filter. Okay. And these filters are such that it integrates to 1. Okay. So, what I am saying is that you can think of d function g as a pretty bad eyeglass. It just fuzzes everything out. Okay. Really, there are billion particles there, but once you wear it, it just blurs things on a scale. And this is this length scale. So, what we are going to say is that we write an equation for fluid and particles resolving everything, and then we take this pretty bad eyeglass and we are going to look at everywhere, so that you only see fuzzed out detail. You do not see anything that is smaller than L. Anything that bigger, when you move around it. So, this is just a mathematical, it's filtering operation. Okay. So in other words, you will do what is called a convolution operation. Convolution operation is you take this filter and you apply it here, you apply it here, you apply it here, everywhere you will apply, so that everywhere you get a coarse grained, you just a fuzzed out picture. When you apply this G on a very finely resolved flow, it will create a much smoother flow, removing all the details that are inside, and that operation is called convolution operation. So, with this defined, everything is ready. We just take our really Navier-Stokes equation, particle motion equation, and we apply this fuzzing operator or filtering operator on it and get final equation. That's the strategy. And that's how your Lagrange Euler equations are derived. Now, in doing this very rigorously, we will know every spot where there is a modeling that needs to be done. You may not apply all those models, but as a course, I want you to know everything that needs to be modeled as this fuzzing operation is done. Now, it is up to you to choose which one to model and which one to throw out, and which model you want to use for the ones that you decide to keep. So, everything hopefully will become clear. Okay? And also I recommend that when we write, we are going to write all the modeling in the book. I have list maybe 10, 12 different things that have to be modeled, because the reason is, whenever you do this fuzzing operation, whenever you do averaging, which is the Reynolds average equation, you know that averaging causes subgrid stress terms or subgrid stress like terms. They have to be modeled. There is a price you have to pay for averaging. When you decide that I am not going to look at all the details, when I am going to look at only the fuzzed out detail, that means you have to do modeling. And we are going to rigorously go through this process. I mean, I may not do it in the lectures, but in the notes. I haven't given these notes, and I will send that later chapters as well, and you can read them. Okay, and you can see what modeling needs to be done. Okay. Okay. So the convolution operation I will define. If you have a function psi, let's say I want to know a fluid property psi. Yeah, I want to fuzz out a fluid property psi. This is fine details that I am not going to compute, but let us say that it is there. So, this may be temperature, or this could be pressure. It is described everywhere in great detail inside the flow. Then you say, first you have to multiply by this filter function. You say that I want to look at it only where there is fluid. I am not going to look at it when there is solid. And you multiply by this filter function, which is a Gaussian. This is the fuzzing out stuff. And you integrate, three-dimensional integrate over the entire volume, and this gives you psi bar of x and t. So, you take a detailed picture, and this is what I was talking about, moving this fuzzing out operator everywhere, and you do the convolution integral, and out comes a really smooth. This guy has filtered psi, has no info below this length scale. Every tiny eddies, tiny wiggles that's there, it's now gone. Okay. So, this is the basic idea. You could do this for particles also. Okay. Instead of IC, I put ID. Later, I will do that. That's how you will get particle average equation also. In Euler-Lagrange, you don't have to do that because we are going to track particles. We only want to fuzz out the fluid part. Okay. Now, you all know Favre averaging. Hopefully, you will know Favre averaging. Favre averaging is nothing but density weighted averaging. Okay. You multiply by density. For an incompressible flow, it does not matter. So, you get Favre average. But these are details, I am not going to worry about this. So, so just an example. Here, look at this red curve. In both these things, I want you to look at the red. No, black curve. Take a look at this black curve. Black curve is the original signal along one line. Now, important thing is that a bunch of places is dead zero. It doesn't have continuous derivatives because you are cutting through some particle. This is, let us say, fluid temperature, and I am just slicing through that. Wherever the fluid is there, it just goes up and down. And wherever I hit particles, it's zero. I mean, I'm not even inside the fluid, and then you go to the other side and then go. So, you can see that the raw data, particle result data, has to know where the particle is, where I'm in the fluid, and so on. Now, once you do the fuzzing operator, the biggest advantage is that it's there everywhere. Inside the particle also it's there. So, that's the biggest advantage of this fuzzing out operator, is that your fluid now is everywhere, omnipresent. So, there is no reason to know, am I in the fluid, am I in the particle, which is what the biggest trouble that you have with Euler in particle result simulation magically disappears. Even though you are tracking particles, now your fluid velocity is everywhere. That is why in Euler or Lagrange simulation, you do not have to care about where the particles are. Of course, you care when you track particles, but as far as the fluid is concerned, you say it's there everywhere. Okay. So, the larger the filter width, you see you go from black to red to blue to green. Green is much filter width, all the little ups and downs, not only the ups and downs, but inside particle, outside particle, everything is fuzzed out, and you get a continuous variable. Now, you do not have to worry about where the particles are as far as the fluid is concerned. Okay. Only you will be concerned only when you apply a two-way coupling feedback force and so on and so forth. But for solving, you can just take a single phase solver and you can use it. That is the biggest advantage of Euler-Lagrange scheme, is that you do not have to worry about resolving some boundaries. So, that is a very important point I want to. So, that is what the basis of how a Euler-Lagrange simulation governing equation are first derived. Okay. Any questions? Yeah.
Sir, I didn't understand the point wherein you have said ki, we have been ignoring particles and the whole domain is of fluid. Can you please re-explain?
Yeah. Look at this black signal. Let's go here. So, ignore the left hand side, that is for a different filter. Let us look at only the right hand side. So, the original psi was having lots of ups and downs. Let us say it is the pressure. It's the pressure inside the fluid. So, out here in this part there is a particle, here there is another particle, and here is another particle. There is no signal. Okay. So in a particle resolved simulation, you will simulate only the black portion outside the particle. Now if you apply a filter, Gaussian filter of a small width, it becomes a red curve. Black curve is this. Red curve is the filtered quantity for a small filter width. The Gaussian is narrow. Now I make the Gaussian a little wider, I get the blue curve. Blue curve is even more smooth. And then green curve, where the filter width is so large that it is able to capture the whole thing. Now you asked, how do you choose the grid? So you can decide if your grid is big, then you are computing green curve. The difference between the black curve and the green curve is you have to model somehow. And that's why we were using Langevin model, because if you really going to compute only green curve and the particle, when you tell the fluid velocity at the particle, you can only give it the green curve because that's what you are computing. But the actual drag should be based on the black curve. So there will be fluctuation, and that's what we try to model in Langevin model, etc. So whenever you do Euler-Lagrange or Euler-Euler simulations, you do averages, and average is very important, because the point I am trying to make is, look at this red curve, blue curve, and the green curve have no zeros. There is no inside particle, there is no outside particle. I simulate everywhere. Okay, that's the point I was trying to make. Any questions on that? Yeah.
Maybe it's just you are trying to consider coarser grid.
Yeah.
So that's why it's just neglecting.
Yeah.
Let's say you have a point. So let's say you increase the grid size, but there is a point on which the particle is there. Then in the green curve also it will be 0.
No, it will not be. It will not be. Okay. Because let's say you pick a point where the particle was. Your green curve is saying this is the velocity average in this region, which includes non-particle place also. So what's wrong with that? I am not saying, when I say, that's the thing, excellent question, psi at a point x, which happens to be at the particle, that psi doesn't correspond to velocity of fluid only at that point. It corresponds to a velocity over a volume of length L, where there is not fluid, there is no fluid, and you are fine.
So maybe you can consider that if we take one point, then 1, 2, 3, 4, 5, and 6 points average together, for example.
No, you see, again a great question. Please don't think of numerical methods at all. I keep saying everything in the last 4 days I am only talking about deriving equations. Now what you put it on a grid, that's a separate questions, and you averaging left neighbors. Here this is a mathematical operation. I am just creating a new function, filtered function psi bar, and I am that's an interesting thing. So what we are going to do is, we take Navier-Stokes equation, which is written for psi, these original variables. The Navier-Stokes is equation written for this, and this equation is valid only outside particles and so on and so forth. Now we are going to write an equation for barred quantities, where it's there everywhere. Okay. Now you can decide whether to put a fine grid, coarse grid, etc. But typically, since psi bar has a length scale of L, why would you put a grid which is 100 times smaller than that? So for example, once you decide to go to green curve, and that's a filtered operation, then you make a numerical decision what grid will resolve the green curve. It's not the other way. You first decide what scale on which you want to filter and represent all the turbulence, and then you ask a question, what grid would do a good job for this one. Okay.
So then in a way what we're doing is we're changing the velocity seen by the particle, as we were related to the discussion earlier.
Yeah.
So then we had to add something to get it back to the.
Exactly, exactly. So, in other words, so what we are saying is that the fluid is being smoothened, coarse grained, whatever you want to call, or filtered, and that is the velocity we are going to compute. And it makes our life easy, mainly because we don't have to solve this equation outside particles. We will solve it everywhere. I mean, you may not realize that that's a massive advantage. In Euler-Lagrange, you are computing the flow inside the particle also. What allows you to do that is this rigorously. I mean, it's not like an approximation, it's just strictly we are saying. But the price we pay is that we decide not to compute the black curve, but we decide to compute, depending on the filter, red or green or blue curve. And then the price we pay is, then we go and look at this particle location around the particle, what the flow, you can get a velocity to be as given by the red curve or the blue curve. You know, it's quite a bit varying. Okay, so that's the point I was trying to make. Then the neglected turbulence you need to somehow take into account in moving the particles. Okay, I talked about this, so I'm going to move. I won't derive this thing, but I will just say it. See, this filtering operation, we are going to apply. We are going to take the Navier-Stokes equation. Let's just take the incompressibility condition, or let's take the Navier-Stokes equation. And we are going to do that filter operation that I talked about. What time? 2 o'clock? Huh? 12 o'clock we need to stop there? Yeah, okay. I will stop in a minute after this. So we are going to, this is how we will, this will give you filtered Navier-Stokes equation. Okay, this is what we are going to formally do. The issue that I will talk about is, okay, how this integral we want to take the derivative outside. So, in other words, we want to, every time we want to somehow rewrite it, this average equation we want to write like Navier-Stokes equation, which would involve that we need to commute integral and derivative, spatial, and there are two rules called Gauss rule and Leibniz rule that allow you to, they will create additional terms, and we will do it. The book is done rigorously, and I will talk about when we get back, rigorously derived mass balance, momentum balance equations. Okay. Thank you.